Alright, the next chapter that we're going to get into is chapter 16, and we're actually going to get through this chapter in 2 days. Because I'm pulling out just the essentials that I kind of think would possibly, you might see one thing or the other. Okay? Alright, so chapter 16 is on acid-base equilibrium. Alright, well, since we're talking about acids and bases, excuse me, how can we define what an acid or a base is? Well, honestly, there's more than one way of defining an acid and base. Okay, one way that we can define an acid substance that increases the hydrogen ion concentration when dissolved in water. Now, base, very similar how we're going to define it, except we're going to change one thing. No, not really. Would it decrease? Yes, but we're not going to use the word decrease. We're going to still use increase in the definition. Substance that increases the hydroxide ion concentration when dissolved in water. I'm going to get the book out just to make sure that I write this next word correctly. Okay. Now both of these are under the I was even right. Arrhenius terminology. Okay, Arrhenius was a scientist that lived way, way, way back in the old days. And he said, an acid does this, base does that. And for a long time, that's all we knew were acids and bases. But in about somewhere in the 1800s, there were two scientists that were still working with different solutions, and they noticed that these definitions weren't helping out with what's going to be an acid and what's going to be base. And two independent scientists. One was English, one was, I think, Danish. Okay? And they came up, working independently, but they came up with the same results, so they came up with a new way of defining what an acid and base is. So we have the Bronsted-Lowry terminology for both acids and base. And what they found out is that an acid is a substance that donates a proton. Okay, now, the way that they represent this proton is by hydrogen ion. Okay, so let's kind of think about that. Hydrogen atom has
Proton, electron.
One proton, one electron, right? Hydrogen atom. Electron spins around. Take away that one electron,
It's proton.
we have our proton. Okay? Not too much different from the Arrhenius definition of an acid, but the base definition changes. They said that a base is a substance that accepts a proton. All right. So if we had since we're in equilibrium, what they're saying is that in this equilibrium reaction, we have acids and bases on both sides of the equation. And we can look at it and identify which one is going to be the acid, which one is going to be the base. Okay, so and the way that we do that is we look to see what's happening from our reactants from the left-hand side to the right-hand side. So if we look at hydrochloric acid, we have HCl goes to just a chlorine ion. So what has happened to HCl? It has donated or accept a proton. What? It has donated because it goes from HCl to just a chlorine ion. So HCl is our acid. Now if we look at ammonia, NH3. NH3, on the left-hand side, right-hand side, we have NH4 with a +1 charge. So it has accepted the base, or accepted the proton, so it is a base. Now we also have acids and bases on the right-hand side of the reaction as well. They are conjugates. Now the word conjugate, what does that mean? You might know. Yeah, they go together. So if something is an acid on the left-hand side, on the right-hand side, its conjugate is going to be the opposite. So HCl was the acid on the left-hand side. Chlorine ion has to be our conjugate base. It can't be a conjugate acid because it doesn't even have any protons to really give. Does it have any hydrogen ions to give out? No. Then if we look at ammonia, ammonia was our base on the left-hand side, so the ammonium ion has to be our conjugate acid. Okay? Any questions with this first example? Let's do a couple more together, then I'm going to have you try a couple on your own. Okay, so what's going to be our acid? Well, let's look at our first reactant. We have HNO2, nitrous acid. On the right-hand side, we just have the nitrite ion. So, has it donated or accepted a proton? Donated. So it is an acid. Now water goes from H2O to H3O with a +1 charge. That is called the hydronium ion. So water is going to be our base. Now on the right hand side, nitrite ion. Well, if nitrous acid was our acid, the nitrite ion has to be our conjugate base. And water was our base on the left-hand side, so the hydronium ion has to be our conjugate acid. You see how this works out? Yes, no? Questions? No questions? Okay. You want to try one on your own? Okay. Now, one thing you're always going to have an acid base on each side. You're not going to have two acids together or two bases on the other side. Okay? All right. Ammonia, NH3, acid or base? Base. Water. Acid. Hydroxide. Conjugate base. And ammonium. Conjugate acid. Is that what we came up with? Yes? Questions? No? Alright, now let's look. Water in one reaction behaving at a base. Another reaction is behaving as an acid. How can this be? Anybody know? Anyone ever heard of this word? About anybody in AP biology or anatomy haven't talked about antiprotic? Okay. Amphiprotic just means that it can behave as an acid or as a base. Most substances are either going to be an acid or a base. Amphiprotic, it can be either one. Okay? Any questions so far? No? Alright, so going along with how water is amphiprotic. Well, if we were to break up water, we would get hydrogen ions and hydroxide ions. Okay, so we said hydrogen ions give us acids, right? Hydroxide ions gives us base. That's why it's going to be amphiprotic. And since this is at equilibrium, what would the formula look like for the equilibrium constant? KOC is equal to, if I remember,
Product of reactants, so it'd be like H plus times OH.
yeah, concentration of hydrogen ion times concentration of hydroxide. Anything else?
And over.
Would it be?
No,
No, because it's a
yeah, liquid.
liquid, okay? Hey, you remembered. That's good. That's good. All right, so yeah, since it's at equilibrium, KC is equal to the hydrogen ion concentration times the hydroxide ion concentration. Now for this one, instead of saying that it's the KC, we call it the water constant, K of W. And the K of W is equal to 1.0 times 10 to the negative 14th. Alright, so since KW is equal to concentration of hydrogen ion times concentration of hydroxide, if we know one of those numbers, we can figure out the other one. Right? Okay, so now this leads us into something I wish I could have got into with Chem 1 last year. Finding concentration of hydrogen ion concentration or hydroxide, or finding, what's called the pH. pH. We've heard about it before, right? Well, what is it? Anybody know?
It's potential hydrogen.
It tells us the potential hydrogen ion concentration. It's actually just a formula. pH is equal to the negative logarithm of the hydrogen ion concentration. So if we know what the hydrogen ion concentration is and we put it into this formula, it's going to kick out just a number. Okay? No unit with it, just a number. And we call it the pH scale. So you might know what the pH scale range is. Close, not 1, but actually 0 up to 14. Okay? So 0 to 14, our range, right in the middle. What would be right in the middle?
Water.
7. Okay, now, if something has a pH of 7, it's considered to be neutral. Anything that has a pH from 0 up to, not including 7. So it could be 6.999999999 infinity. It would still be considered an acid. Anything higher than 7, all the way up to 14, is considered to be a base. Okay? Any questions there so far? No? All right. Calculators. If you have calculators, let's go ahead and get them out. If you need to borrow a calculator, I'll get those out. Okay, so first example, what is the pH of a solution that has a hydrogen ion concentration of, let's say 3.14 times 10 to the -2 molar. Okay, so if you have one of these calculators, you might be able to put it in as you see it. So, pH is equal to negative log of 3.14 times 10 to the -2 molar. Put it in like that. Now, if you have one of the older scientific calculators or one of the how do I want to say it? I like what Sarah has. Hold up here, Sarah, please. One of those, you have to put it in backwards. So you'd have to put in the concentration first, then hit the log button, then hit the negative sign. Now, if you have the other ones, you should be able to, how we write it down as a formula, that's how you should be able to put it into the calculator. So go ahead and try to put it into your calculator real quickly. Okay, what are we coming up with for a number, please?
1.503.
Okay. 1.50? Is that what other people are coming up with? Okay, so now if the pH is 1.50, would you think it's very acidic? Yeah. Look, for acids, the closer we are to 0, the more acidic it's going to be. Okay? For bases, the higher we are, or the closer we are to 14, the more basic it's going to be. Now on the pOH scale, pH of 1.5, that hurts. That'll probably burn, that'll take away skin. Okay? When we get closer to 14 on the pOH scale, that's going to hurt. You can dissolve a body. Okay? Lab. All right, so now the closer we get to 7 on either end on the pOH scale, might get a little tickle. Okay? Now, just to kind of give you a heads up, there are some acids that can actually give you a negative pH. Their concentrations are so strong that it will give you a brief negative pH.
Give us an example.
Sulfuric acid, battery acid.
Oh.
Okay, battery acid, right here, it flirts with 0 sometimes. If you have the right concentration, it will give you a negative pH. So that's one I wouldn't really want to mess with. Hydrochloric hurts. I've had it on my skin. It's like one little drop of hydrochloric acid. I'm going to hold up my 2 fingers so I'm not flipping you off because it was the middle finger. But back in 2000 in analytical chemistry, one little drop of acid touched right below the cuticle. So if you look at my finger, I have a little bit of discoloration right here. And it bubbled up instantly. I go, Dr. Jim, I got some acid on my finger. He goes, okay, yeah, go wash your hands real quickly because wash your hands with soap. Soap is a base. And it came into contact with the acid and it neutralized it. So I got it to close to pH of 7 again. Now, of course, yeah, it stays like that forever and everything, just like any other chemical scars I have on my arms, hands, and everything like that. Okay? So, do we need to do another example? We kind of see how this works out. Good to go? Now, what if we wanted to figure out what is the hydrogen ion concentration when we're getting the pH? Well, look at your calculator. Look at the log button. What's right above the log button? I mean, right above the log button. 10x? Does everybody see that? Okay, that is called the antilog. So if we wanted to find the hydrogen ion concentration, we would take the antilog of the negative pH. Alright, so let's kind of do a real quick example of that. What is the hydrogen ion concentration of a solution that has a pH of, Ethan, give us a number please, from 0 to 14.
0 to 14?
Yes.
4.
Well, let's go a little bit higher.
4.5?
Go higher.
Okay, 6.5.
Okay. Okay, it's 6.5. Okay, so hydrogen ion concentration is equal to antilog of a negative pH, so 10 to the negative 6.5. And just like before, if you have one of the nice, scientific calculators, you have your graphing calculator, how we write the formula down, that's how we put it into the calculator. If you have one of the older version calculators, you gotta start with the pH, hit the anti-log button, then the negative, or negative 6.5, then second function anti-log. What are we coming up with for a concentration? Give it to me in scientific notation, please.
3.16 times 10 to the negative 7.
Okay. Jacob says 3.16 times 10 to the negative 7. Now, since it is concentration, we have to have molar with it. So how many people are coming up with 3.16 times 10 to the negative 7 molar for concentration? All right, so now if we look at the two concentrations, first example, it was 3.14 times 10 to the negative second, right? We had a pH of 1.50. We go to a pH of 6.5. What's happening to our hydrogen ion concentration? It is decreasing. Okay? So the higher we go, the smaller the hydrogen ion concentration is going to be. Okay, any questions there? Good to go? Now, there is, since we have the pH scale that deals with, hydrogen ion concentration, there is a pOH scale. Okay, now the pH. Now to find the pOH, very similar to finding pH. Guess what we're going to change out? Yeah, so pOH is equal to the negative log of the hydroxide ion concentration, yes. And we do have a pOH scale. Guess what the pOH scale range is? 0 to 14. Guess what's going to be at 14? Or guess what's going to be at 7, excuse me. We're going to be neutral. Now, from 0 up to not including 7, in this situation it's going to be a base. Anything higher than 7 up to 14 is going to be an acid. Why is that? Anybody have a thought? Ethan?
Because it's the inverse of the pH scale?
Yeah, because since we're looking at the hydroxide concentration, and what we saw is that the higher the concentration is, the lower the number is going to be when we find the pH. So in this case, if we're trying to find the pOH, more hydroxide ion concentration is going to give us a smaller number. Okay? All right, so since both scales are from 0 to 14, if we knew the pH and we know the pOH, and we add those two numbers together, guess what they're going to be equal to? No? 14. Because since both scales go from 0 to 14, if we add the pH and the pOH together, they're going to be equal to 14. Okay. Now, one of the things I really like about this chapter is that with some of these problems, when you're trying to find pH, pOH, hydrogen concentration, and hydroxide, there's more than one route that we can possibly take to find this information. Okay? So let's kind of look at an example of that. Bless you. What is the pH of a solution that has a hydroxide ion concentration equal to, let's say, 8.92 times 10 to the negative 10th molar. All right, so one way that we can possibly figure this out. Since we have the hydroxide ion concentration, we can first figure out what our pOH is. So pOH is equal to negative log of the hydroxide concentration, negative log of 8.92 times 10 to the negative 10th molar. Okay, so why don't you go ahead and put that into your calculator. And see what we come up with. Anybody of interest in telling me what you came up with?
9.05.
Okay. pOH 9.05. Everybody else kind of coming up close to 9.05? What'd you come up with?
I don't know, it was like 7 something. Oh, that was it.
Yeah. What were you doing wrong?
I wrote down to the negative 8.
Okay.
I don't know why.
Yeah. All right, so now, since we have our pOH, and we just learned that the pH plus the pOH is equal to 14, we can use this formula to find the pH. We can say that the pH is equal to 14 minus pOH. 14 minus 9.05. What?
4.9.
And Stephen says 4.95. Okay. Pretty easy, right? Or another route that we can do with this. Since we are given the hydroxide concentration, constant is equal to the hydrogen ion concentration times hydroxide concentration, we can find our hydrogen ion concentration by taking the KW divided by hydroxide. Okay, so KW, 1 times 10 to the negative 14th over 8.92 times 10 to the negative 10th molar. What are we coming up with? Anybody? Anybody?
One point one two times ten to the negative.
Anybody else coming up with 1.12 times to the negative 5th? Okay, so now that we have our hydrogen ion concentration, pH is equal to negative log of 1.12 times 10 to the negative 5th molar. And I'm coming up with a pH of 4.95. Okay? Questions? Any kind of questions? No? You kind of see and understand how to use these formulas? Okay, so what I'm going to do is I'm going to go ahead and I have an assignment ready for you, kind of just the stuff right now. Take the rest of the time in class to work on it. We all get it done. We'll go over it before we leave today. Okay?